We are live, Priyesh.
Yes, sir.
Yeah. So good afternoon, everyone. Welcome to this live tutorial session aerodynamics of unmanned aerial vehicles and drones. Our host is Mr. Priyesh and Mr. Rahul are here with us. So please feel free to participate and make the most of this session. Thank you. Over to you, Priyesh and Rahul.
Thank you so much, sir. Thank you.
Good.
Welcome everyone. We'll start with today's tutorial session. So, I hope you have gone through the tutorial one. Uh, if not, no issues. We'll cover tutorial one overview as well today. And let me just share my screen. So, my screen is visible, right? Can anyone confirm?
Yes, Priyesh, your screen is visible.
All
Yes.
right, all right. Let's start with today's session. So today's tutorial session is on fixed wing UAV design and analysis. So it will be conducted by me, Priyesh and Rahul. So overview of this tutorial. So it will be around, it will be from 2 to 5. So we'll have some 15-20 minutes break in between. So we'll start with OpenVSP basics. This was already done in tutorial 1. So we'll not go in detail. We'll do CFD analysis. We'll do initial weight estimation, which was not done in the last tutorial. Performance analysis, basic part was done. Now we have to integrate somehow this performance analysis and weight estimation together. We'll do control and stability analysis as well. And then Rahul will take over the ANSYS Fluent. So whatever model we design today, he will do CAD cleaning and preparation, meshing, solving, and post processing. So for OpenVSP, so this was the I have shared you some. I will share this PPT as well with you guys, so you can concentrate on this session and do this. And this will be also uploaded on the YouTube. So concentrate on this session, and then when you do practice, you can uh, relook the YouTube video and do your homework as well. So OpenVSP, some links. So last time, how to download OpenVSP, VSP Airshow. Last time VSP Airshow was I did not cover, so I'll just go to VSP Airshow. So if you go to this link, so whatever model we design, we can upload it in an open source open community. So like GitHub, people upload their codes. So in Open VSP Airshow, people upload their VSP CAD design. So let's say if you go to start exploring, you take, so these are the models people have uploaded. So um, you can just download these and use as per your requirements. Tutorial I have already told you, there is a YouTube library. You can watch YouTube videos. Next is why we are doing this CFD analysis. So once we get our CFD loads, how we will use those CFD loads. So we have CL, CD, CM with us. With this, we will have some initial L by D with us for the model. We have some initial weight estimation. With that initial weight estimation, we'll do the performance calculation. So what performance calculation I will tell you, they have to converge. So if I have some initial weight estimation and let's say initial weight came out to be 10 kgs or 20 kgs, let's say it is 20 kgs. So now it will go to performance matrix. It will calculate the performance at what velocity it needs to fly, what is the power requirement. There again, new L by D will be generated. So now I have new L by D. So this new L by D again will go to my weight estimation. Then again, my new weight will come. So this has to converge. How this convergence will take place? We have a MATLAB code. I'll show you. And what performance? parameters we need. So these are the performance parameters what uh, in early stage design we generally look at. So we see my neutral point, we see my power requirements, CLCD, my all up weight, power loading, wing loading, V cruise, then my angle of attack, how at what is my cruise angle of attack. So these are some and these formulas you will get in your standard aircraft design books. So next we'll see what is the configuration selection. So let's say I have multiple configuration. So I have given reference also. You can go to the reference. So this is very good reference for when you start your UAV design. So I highly recommend you to read this paper. So this is a performance analysis and design of loitering munition. So what they have done is they have um, they have taken conventional fixed wing, canard, delta wing, cruciform, tandem, rotary craft, whatever was available in the market. So they have done the performance and the design analysis of it. So they have plotted many kinds of empirical formulas. We are going to use those as well. So these are some. So you can see these are some different kinds of UAVs. We have some battery powered, battery plus piston, and then piston. Maximum takeoff weight versus the payload weight. So this is how the trend looks for recent UAVs. Again, they have given some empirical formulas how to calculate your all-up weight and how to calculate your endurance, how to calculate your dive speed, how to launch your UAV, canister launch or rail launch. So I highly recommend you, and they have taken also some case studies in this. So you should definitely go and study this research paper. It's openly available. You can just download this paper. So in this paper only, you have what exactly is your purpose? Long loitering endurance. You want more endurance. You want more terminal dive speed. You want precision trajectory control. So based on that, you can select your configuration. Now comes the main part, initial weight estimation. So in this paper only, they have given this formula. This is payload versus endurance into is equals to F. This is the power equation basically. And they have given and they have to call the trend lines of it and given the numbers here. We can plot these numbers and find out how my UAV will perform. So I can go to, so this is the formula what we will use. So let's say payload is 2 kgs, my endurance is 120 minutes. So what will be my all up weight? So this is the basic equations you can use. Now this study, now one more thing you have to take care of is that this study was done back in I think 2022. Okay, so now it's 2026. There will be a huge development in the UAV technology. So this numbers might not be relevant. So what your task is to do this study again with latest UAV in the market, plot these results, get these new number and get the initial weight for your design. So if I simply take these formulas, I have payload weight for 2 kgs, endurance of 120 minutes. Then my configuration weight will be if I'm selecting cruciform, it will be a 15 kg. For conventional, it will be 14 kgs. Tandem, some 30 kgs. Delta, 21 kgs. If I uh, if I increase my payload, you can see how my aircraft weight is increasing. Formula is simple. My payload into endurance divided by this F and under root of 1 by E. So simple formula, you can plot this in Excel and get the all up weight. This is the all up weight estimation, basic, very basic, if we're using the empirical formulas. So what is the disadvantage of this is that you don't have uh, the this formula does not incorporate the size of UAV. Let's say if I change my aspect ratio from 10 to 5, how my weight will change. If I increase my cruise speed from 20 meters per second to 30 meters per second, how it will affect my design or how it will affect my all of weight. This equations does not capture those. So this is the biggest disadvantage of this. So next, what we can use is we can use Raymer's iterative based weight estimation. So this is also empirical based. So they have all the trend lines for most of the UAV type. So what UAV type they have? Let's say they have fighter jet, jet trainer, ultralight, agriculture, aerobatics, flying boat, UAV jet, UAV prop. So they have all the trend lines for the empty weight fractions and the all up weight. So this is the empty weight fraction on the y-axis. On the x-axis, we have all up weight. So my UAV will be uh, my UAV will contain payload weight, then all the electronics, empty weight, fuel weight, or battery weight. So these are the weights a typical UAV will carry. And once you reorganize all these equations, you get the formula something like this, which is my W naught is equals to W payload divided by 1 minus battery mass fraction. So this is BMF, battery mass fraction, minus my empty weight fraction. So I already have some relation between empty weight fraction, these relations. I need some relations for battery mass fraction. So there are no relations. You have to get your battery mass fraction. So it will depend on your power requirements. So this is the equation I will use. This is just the power divided by uh, uh, power multiplied by endurance is my energy density, and this is the similar formula, slightly different. So this equations I can use to calculate the all up weight. How? We'll see. So I'll just open the MATLAB. So this is the, so let's say I open it like this. So in this I will take, let's say, my payload weight as 1 kg. My battery weight fractions, I will assume let's assume it as 0.2. A and C are the coefficients uh, in this graph you see. So this is the A and C. So these are the power coefficients. So for, let's say, ultralight, I'm taking 0.673 and C is minus 0.05. So ultralight is somewhere around this line. And right now, battery mass fraction, I'm taking it as constant. So my initial weight, I need to estimate some initial weight. So generally it is 4 times of your payload weight. Some tolerance, 1 e power minus 6. Right now error is 1. Maximum iteration I'm giving. Now here my loop will run. So my battery mass fraction is 8 multiplied by W naught to the power of C. New weight will be the formula which was given by Raymer, and it will do the calculation. It will find the error. If error is greater than 1 e power minus 6, this loop will continue to go on. So let's say if I run this, I have my converged in 10 iterations. My all up weight is 5.4 kgs. Empty weight is around 3.3 kgs, and battery weight is coming around 1.09 kgs. Now, let's say if I increase my payload to, let's say, 2 kgs. If I run this, again, I get some new weights. Now, problem with this formula is I don't have my I don't have information for my cruise velocity, for my power requirements, for my endurance. So all this is captured in this battery mass fraction, which I'm taking 0.2 as a constant value. So this is very basic. You cannot use this because your battery mass fraction will not be a constant value. So if I change this to 0.1 and then run, my numbers will change, right? Why my battery mass fraction is changing? Because let's say my so battery mass fraction depends on your it depends on your endurance, velocity, all your efficiencies, L by D. Your ESB is your battery specific density. So if you take a good battery, a battery with higher energy density, you will have lower battery mass fraction. So every information what we need is captured in this battery mass fraction. So this cannot be constant. So next step, we have to incorporate this form. So in this, I have incorporated the battery mass fraction formula. We'll go through the code together. So let's say I have a payload of 1 kg, L by D is 10, velocity of 60 meters, say 60 kilometers per hour, endurance of 1.5 hours. Now you need to take care of all the units what they are using in the Raymer. So whenever you are using the formula, go to this book, make sure that whatever the way he has derived the formula, he has some units in his mind. So you take those units. So all efficiencies I have taken propeller efficiency of 0.75, battery efficiency of 0.85, battery density of 300 kgs, watt hour per kgs. Again, A and C value. My okay, one more thing to see if your result, if your code is running right or not. So if you change this initial guess, so right now it is 4 times of payload, it is coming to be some 7 kgs. If I change this to 5, it should not change. Even if I do 50, if I run, it should not change your all of it. Okay, so this is one just a test case you can run. Again, same equations here. Again, same equation. Now here, instead of taking battery mass fraction as constant, I have incorporated the equation. What equation? The same equation what Raymer has derived. So this equation I have substituted here. So I have battery mass fraction. Again, my new weight will be calculated, and this loop will run until my solution is converged. That means the error between my new weight and old weight is less than 1 e power minus 6. Uh, 1 minute. Hmm. So if I run this, now you see I have some different weights, 4 kgs. Now let's say if I change my L by D to 12. So what do you think? How my weight should look like? It should decrease, right? I'm increasing my L by D, so my weight will decrease. If I increase my cruise velocity to 80 meters per second, my weight will increase. My power requirement is more. My battery weight will be more. My total weight will be more. If I increase my endurance from 1.5 to 2 kgs, if I run, my weight will increase. I need to fly for longer time. My battery weight will increase. My all of weight will increase. If I reduce my uh, battery density, so I need to carry more battery weight. So let's say I go for 250 watt hour per kg. So my all of weight will increase. So my all of weight got increased. So um, this is how the weight estimation is done for your UAV. Now again, disadvantage for this code. So there was some disadvantage in the earlier code. We fixed it in the next version of code. Now there is some disadvantage in this code which you need to uh, take care. I'll tell you how to do. You need to implement this. So right now we are taking this L by D of 12, which is constant, right? But this will not be constant value. I told you weight convergence, weight convergence, as soon as my weight is estimated, I have new weight. With that new weight, new performance matrix will be generated. I will get my new L by D. Why new L by D? My lift is new. Why? Because my weight is new. So in cruise condition, my weight is equals to lift, so my L by D will change. So this L by D will change, again my new weight will change. So this has to converge. So that's why taking this L by D of constant value is wrong. So you need to incorporate this L by D inside the loop. You need to update L by D for every iteration. So we will go back to our Excel sheet. So last time we did the CFD analysis, we have some inflow conditions, some Mach number reference, Reynolds number calculations. So this was my alpha sweep. So angle of attack versus CL, CD, CMY. So this is how my trend was coming for. Now this plot is uh, CD versus CL. So I'm sorry, this is my CL value and this is my CD. This is my CD. Okay, I'll plot this again. So I have some angle of attack. I have some alpha sweep here. So let's say I plot CL versus CD. This is the plot. I'll plot the trend line, polynomial, display equation to the chart, and R square value. So this is the equation. So this is my CL. This is my CD. So here I got the equation which represents, sorry, which represents my drag polar. So Y means my CD, X means my CL. So this is the drag polar equation I'm getting. This drag polar equation, we go to performance analysis. This was done in tutorial 1. I hope you guys remember. So what I have done here, I have first velocity. It is going from 10 to 50. I'm calculating the cruise CL. So cruise CL formula is CL is equals to 2W. So lift is equals to W for my steady state level flight. 2W by rho V square S. So same thing I have done. 2 into W. So W into 9.81 divided by rho divided by V square divided by S. So this is how I get my cruise CL. So I get cruise CL. Now I want my cruise CD. So for to calculate cruise CD, the equation what I got from my CFD analysis, I will take that. So this is my CD, same 0.04 into CL square plus 0.04 into CL plus my CD. So this is how I calculate my cruise CD. Now drag is my half rho V square S into CD. So I calculate the drag in Newton. I calculate my power. Power is my velocity into drag. So I get my power. I can calculate my L by D from here. This is my cruise L by D. So it goes from, so I can just simply plot CL by CD. I get my L by D condition. You can plot CL power 3 by 2 by CD. I can plot this or this as well. Now I have some L by D. Now see what happens. Why I'm telling you this cruise L by D is important. Let's say if I change this all up weight. So right now it is 37.96 kg. If I change this to let's say 50, my L by D changes. Right. Let's say I want to what velocity I need to fly at. So I will plot velocity versus my L by D. So this is my velocity, and this is my L by D. This is my L by D. So if I change my weight, So let's say it goes from 40. You see my L by D graph is changing, my cruise velocity is changing. So I want to cruise at maximum L by D, let's say. So I will cruise at around 35 meters per second. If I change this to 30, now I have to fly at 30 meters per second. So you see in this code, if I change my L by D, my cruise velocity will change. So my L by D is changing, my velocity is changing. So in battery mass fraction, my velocity is changing and my L by D is changing. So this thing you need to incorporate in this code. So I'll share you the code. You need to update these equations such that you update L by D and velocity for every iteration. So this was all about the weight estimation. Now again, problem with this code is we are using some empirical formulas. So you see, we are step by step, we are getting some problem in the code. We are updating it in the second code. Now what problems exist in this version of code? Let's say we incorporate this updation of L by D and updation of velocity and get a new all of weight, but still the problem is we are using these equations. Now these are old equations. The battery mass, the empty weight fractions, what we are using, these numbers are old. So we need to have some new equations for this, but we don't have data for the latest UAV in the market, so we cannot really make these equations. So the next method is direct weight estimation method. What weight UAV will carry? It will have payload weight, battery weight, propulsion weight, structures weight, subsystem weight. So payload weight is fixed for me right now. It is, let's say, 1 kg or 2 kg. It is mission dependent. So it can carry a sensor or camera or mission specific equipments. Battery weight, we are calculating how from the battery mass fractions. That is fine. Now in this, this is fine. It is updating. If I change my aspect ratio also, it will have it will change the drag. If I change the aspect ratio, if I change the aspect ratio, all my aerodynamic loads will change, my alpha sweep will change, my drag will change. So if my drag is changing, all drag is changing, my power will change, my L by D will change. So it is incorporating the body effects. So if I change my configuration, all this will take care. But what is the bottleneck now? This formula, empty weight fraction. It is not having any information. Uh, so to incorporate more accurate weights, we do direct weight estimation. So we have payload weight, battery weight. As I said, battery weight we are getting from endurance and energy requirements calculation. Propulsion weight. So let's say I'm using electric motors right now. So again, for some calculation, I have to depend on my empirical calculation. So what I will do is I will find all the motors available in the market and I will plot it, peak power versus my all of the motor weight. So I get some trend line. So whatever peak power requirement is for my mission, I will use that. And for ESC calculation, same thing I will do. I'll plot all the ESCs available in the market for peak current rating and my ESC weight. I'll get some trend line. So this is my propulsion sizing in equations I will use. So this was all about propulsion. Now structures weight. So structures will be, uh, you can say as empty structures weight. So for structures, we have skin, spars, and ribs. So for skin, what we will do is my whole aircraft will be a thin shelled. So it will not be a solid body. So I will define one term which is known as aerial density. So let's say if I have a skin of thickness of 0.5 mm and I'm using a carbon fiber material and the density of that material, volumetric density of that material is 1500, then my aerial density will be density multiplied by skin thickness. So it will be a aerial density. So how will I calculate the weight of the skin using OpenVSP? So what I will do is I'll open OpenVSP. Let's say I add a fuselage, I add a fuselage, I add a wing, I add a wing. Okay, let's say uh, I have these two parts in the UAV. So what I will do, I will go to mass properties. I'll go to mass properties. There's an option known as thin, include thin shell. So this is thin shell. Density will be zero. Why? Because my volumetric density is zero. I'm using my aerial density formula here. I need to plot mass by area. So how much mass is present per unit area. So that this is known as aerial density. So you can see aerial density. So this number I need to get. So what I will do is, let's say if I take these numbers and I multiply this, so 1500 multiplied by 0.5. So 1500, 1550 multiplied by 0.5 mm divided by 1000 to convert it into meter. So this is some 0.775. Yeah. So 0.77. Again for wing also, mass properties, density 0, include thin shell, mass by area, it will be 0.775. All right. We go to analysis, mass property and compute. So you get total mass of the UAV as 233 kgs. Now this only includes the skin of the UAV. It does not include spars or ribs. You can validate this formula as well. Uh, you know the volume of sphere, right? So let's say I add a sphere. Um, there was some sphere. Okay. So this is the sphere I have. This is the sphere. Same thing I will do. I'll go to mass properties. Now let's say I don't, include this thin shell and only see the density. So let's say I'm using a steel ball. First, I'll define the diameter. So it is 1 meter, 1 meter, 1 meter. So let's say the radius is 1 meter. Density of steel is some 7850. Okay. This is the density. Radius is 1 meter. I'll go to mass properties, compute. So I get the mass of the sphere. Now, to validate this, I'll just simply do volume of sphere. So this is the volume of sphere. So my radius was 1 meter. My radius is 1 meter. My volume is around 4.199. So again, 4.19 multiplied by the density is this one. I will get the mass of. So 32891. And we got 32450. So this difference between your calculated mass and this numerically calculated mass is because of truncation error. So you see the number of slices here. So what it is doing, it is slicing this sphere into 20 parts and calculating the volume. So if you increase this, the accuracy will increase. So similarly, you can try with the hollow sphere. So take the formula, you know the formula for hollow sphere. You give the areal density, give the thickness of shell, and validate this with your results. So from this, we can say that we can use this to calculate our skin mass. So my skin mass is calculated. Now to calculate the ribs and spars, we use the Goodmanson formula. So I'm not going in detail with this. So I'll just give you the overview. So here you can see that this is the airfoil. So Goodmanson has generalized, idealized this airfoil. So this is the skin of the airfoil, thickness of skin. We will consider one spar as the shear web, and the and area will give as a cap. So with these formulas, you can find the weight of the ribs and also the number of ribs. It will depend on your aerodynamic load. So UNZ, this is your load factor. W naught is your all up weight. Tau max is your uh, the shear stress, maximum shear stress for your material. And when you apply all these equations, you can get the weight of the ribs, weight of the spars, and finally the all up weight of all, sorry, the structure's weight of the structure. Now, this was the direct weight estimation method. So structure weight and subsystem weight, controller, pitot tube, power distribution board, GPS, servos. These you can take the assumption of 15% of your all up weight, or if you have available, if you have these parts available with you, you know what parts you are going to use for your UAV, you can simply take those and directly add this to your all up weight. Now, why this uh, updation was required? I told you, right? These are all old equations. These are all old equations. Why it is a problem to use these equation today? So this is why it is important. So you see the same graph, what motor versus the peak power of motor is plotted in 2019. The graph is something like this, and the same graph is plotted today, the 2025, and the graph is something like this. So if you see for the same motor weight, for same peak power, the motor weight is around 1 kgs. For same peak power, for in today, my motor weight is less than 1 kg. So it is almost 0.7. So you see my power to weight ratio is increased. So we can say that the due to the advancement of UAV technology, motor technology, my uh, the power to weight ratio is increased. So that's why it is important to update all these equations. So this is just for motor, for ESCs, for in fact for the composite material, or the or these UAVs as well. This was done in 2022. Now it is 2026. So many updates would be done in the technology. So you need to make your own plots. You need to make your own equations, get your own trend line, and calculate your weight. So this was all about the weight estimation. Uh, some I will share these codes with you. This code, and the third code you have to make, which is update this L by D and velocity for every iteration. For every iteration. Next is I will just give you the overview of design and optimization. So let's say to define any wing, what parameters I want. So I have SREF, I have some dihedral aspect ratio, sweep, twist. So these are okay. I defined a wing. I can define span, area, taper ratio, root chord, tip chord, sweep. twist, and dihedral. So these are some design variables for your wing. If you change any of these, my wing will change. So what wing will give you the best, the best performance or least weight or more cruise speed. So you can perform this design and optimization study. You can divide your, you defined your design variables. So let's say I for wing, these are my 6 design variables. For airfoil level, I can define my thickness to chord ratio, the thickness to chord ratio location, my Y camber, my X camber. So this defines my airfoil. I go from I define lower bound and upper bound for this. So let's say SRF goes from 1 meter to 4 meter. My aspect ratio goes from 7 to 15. So this is the bound I need to define. I divide this up lower and upper bound into, let's say, 50 parts. I run 50 design points. I generate this kind of plot. Total weight versus my wing loading. So this curve will look something like this. So depending on your wing loading, whatever wing loading you choose, you have the results with you for all up weight. So what this is the converged all up weight versus the converged wing loading. Not the part of this course or this. Just I wanted to give you how the design optimization looks like. So this was all about the initial weight estimation. The VSP arrow was explained in the last video. Open VSP basic was also done. Performance analysis was done. Now stability and control analysis. Now in stability and control analysis, will not go in detail. I'll just give you some basic overview. So what things in early stage design we need? We need neutral point location. We need static margin. We need stability derivatives. We need control derivatives. How to generate these? So let's say I have I have made one aircraft. So maybe we can make this aircraft together. Let's say I close this. So so it will give you the overview also of OpenVSP. So let's say I add a fuselage. Right now the length is some 30 meters. I will reduce the length. I'm just using this scale option here to reduce the length and the diameter at same time. So let's say 0.08. So my now length is some 2.4 meters. Okay, that's fine. And I will add the wing. Okay, sweep should be 0. I will turn on taper ratio should be 1. I want aspect ratio. Let's say span. So span of, let's say, 1.5 meters. Taper ratio of 1. So this is the UAV. I'll just give the X direction. I'll add the another wing. So I'll make a tandem wing configuration. So I'll copy this, paste. I'll shift this backward. Now I will give the Z location, Z direction, so that the aerodynamic interference is less. I'll, in, I'll increase the 0 point, let's say 0.4 or 0.5. My aft wing will be minus 0.05. Okay, so this is how the UAV looks like. Shade, let's say. Airfoil I will not change. Now this is the UAV. So I'll rename the fuselage. This will be wing forward. So wing for. This will be my wing aft. Wing aft. Right. So we made this UAV. Now we will do the aerodynamic analysis. So I'll go to analysis, VSP aero. Now the reference area and reference length. I'll select model, and then again I will go to manual. Now this is the surface area of one wing, but we have two wings here. So this will be multiplied by 2. So this multiplied by 2. Okay. CREF, it has already got from the model, BREF and CREF, so it's fine. CG location, important for the stability analysis. Right now, we will analyze at 0, 0, 0. So this is fine. Angle of attack goes from -4 degrees to 10 degrees. Now Mach number calculation. So my velocity is right now 30 meters per second. Temperature is 303.16. Some viscosity, rho 1.225. So what will be my Mach number? It should be a formula. Okay. Yeah. Oh, this is my MAC, mean aerodynamic chord. So my mean aerodynamic chord now is 0.226. So I'll copy this. It is 0.226. So my Mach number will be velocity divided by under root of square root of RT gamma RT. So my Mach number is 0.086. So my Mach number is 0.086. My Reynolds number calculation formula is rho VD by mu. So rho into velocity, D is my mean aerodynamic chord divided by mu. Mu is my viscosity. So my Reynolds number is 4.67 e to the power 0.5. So I'll copy Reynolds number, paste. So this is my Reynolds number. Alpha goes from -4 degrees to 10 degrees. Let's say I go 14 degrees. I need at interval of 2 degrees. So 14 plus 4 is 18. 18 by 2, 9 plus 1. So 10. So between -4 to 14, I have 10 points. So it will be -4, -2, 0, 2, and so on. Then I'll click prepare solver. First, I'll save this file. Save. I'll go to the location. You go to the location. I'll just update the old model. Prepare solver, launch. I'll wait for a while. So you can see it is done. Now where to find this? It is in the wherever we saved the VSP file, there one polar file will be generated. So here is the polar file. So right click, open with notepad. So this is the all the data. So copy. I'll go to CFD analysis. I'll paste. So I'll paste all this data here. So all this data. And what important parameters we need? We need angle of attack. So we need CL total. So I'll paste it here. I'll need my CD total. I'll paste it here. And my CMY. CMY is my pitching moment coefficient. So CMY total. So paste. So this is my new drag polar. I'll copy this As we are doing stability analysis, we'll go to stability and we will paste it here. Okay. Now let's plot angle of attack versus my CMY value. CMY total, insert line graph. This is 0. Angle of attack versus CMY. So this is how I get my graph. So it is stable configuration. Why? Because my CG is on 0, 0, 0. So at the time of analysis, what we did here, we told that my reference point, that is my CG, is at 0, 0, 0. So fuselage. So fuselage knows. So this is the reference point. So right now my CG lies here, this point. So it is a nose heavy. So definitely it is going to be a stable configuration. Now what I have to do is I have to shift this CG backwards. So from 0 to, let's say I go to 0.1, 0.2, 0.3, 0.4 till the last. So my fuselage location is 2.4 meters. So let's say I do 4 times. So 2.4 divided by 4. So I go 0.6, 1.2, and so on. So I will change here X location 0.6. I'll run the same thing. Now this is one way. Second way is you calculate all the aerodynamic loads at your CG location and then shift your all the movements to the point you need. We'll do that also. So it is generated. Again, you open the polar file. It will be updated. Copy Excel and paste. Again, plot. So let's say I plot this, select data. So this data was CG is equals to 0, 0, 0. Okay, CG is equal to X equals to 0. Now again add my CG location is 0.6. X will be my angle of attack. My Y will be my CMY total. So what do you think? How the graph should look like? My stability should decrease. So let's see. It got increased. My stability got increased. Why? 0. X direction is 0.6. So this is positive X. So if I increase my X here, so it should decrease. But it is showing us my stability got increased. Okay, let's try some other. Let's do it at 0 again. See, launch. Again, I go to this polar. It will be updated. I'll paste. I'll again plot. Select, add, Angle of attack versus my CMY. Okay, see, it ideally it should give us the same results, but for some reason it is giving us different results. So maybe the solution is not converging, right? Okay, I think we have not done prepare solver. So that is the reason. So let's do it again. So I'll just save this, save ESP arrow 000, prepare, launch. So the third analysis and first analysis should give us the same results, but still they are giving us different results. We can see, we can plot angle of attack versus CL total also and see if anything is there. Yeah, see, it is giving us different results, so maybe some problem. Okay, so now let's say I copy this, again paste it here. So I think this should not, they should be same.
The second plot you are choosing is CDT total.
Oh, I'm sorry, CD2. Yeah, now it's fine, I think. This one, this, and this. Now I think it's fine. So let's do this, guys. Let's do this again. I'll delete all. Okay. So this was my angle of attacks. Sorry, this was my CG location 0. This was my CG location 0. Now I'll change the CG location to, let's say, 0.6. Prepare solver, launch. Now if I plot this versus my CMY, I'm getting something like this. Okay, it is done. Reload, yes, copy. Now again I will plot, add angle of attack versus my CMY. Hmm. See, my stability is decreased now. So that's what we were expecting. As my CG location moves backwards, my um, stability will decrease. Now we'll run for 1.2. Now we run for 1.2, prepare solver, launch. Now Now you guys think that this is a very tedious job to, shift from CG location from 0, 0.6, 1.2. So what other method we have? What we will do is we'll use parallel axis theorem to shift all the aerodynamic loads from your nose to some other location. So what I will do, I'll copy this angle of attack. Okay, let's not copy. I'll make another column CMY X. Okay, I'll define one term known as XCG. Let's XCG. So I want to move my CG location by how many, like in X direction, how many meters? So let's say 0.6 meters. My MAC is 0.226. 0.226. Okay, the results are there. We'll plot the results. Copy. So if I plot this, I think it will be unstable configuration now. So angle of attack versus my CMY. You see now it's an unstable configuration, 1.2 meters. So what do you think my neutral point location will be? It will be between 0.6 and 1.2. So around let's 0.8 or 0.9 will be by neutral point. So neutral point will be around 0.8 meters. We'll find this neutral point. So what I have done is I'm calculating the moments for that location now. So what I will do, I'll if we are shifting movements and force from one location to other location, what you have to do, you have to directly add the movement. So I will directly take the CMY. So my CMY is this one plus this plus my force in Z direction. So my force in Z direction is this one, CFZ total. So F means my force, C means coefficient, FZ is in Z direction. So force in Z direction. So this multiplied by how the moment arm, the how many how much distance we are shifting this force to this from this point to this point. So multiplied by this CG location. Now divided by, as this moment is non-dimensional, we need to non-dimensional this 0.6 meter also. So we'll non-dimensional this with my mean aerodynamic chord. So mean aerodynamic chord. So this will be F4, as this is a fixed cell. This will be also a fixed cell. Enter. Let's test this. Now we will plot, select data, add angle of attack versus my new CM. So you see they both are overlapping now. My yellow and orange, my new graph. So this one and this one, I'll remove this. Okay. So these two are overlapping now. What are these? Orange one was when I calculated in OpenVSP for CG location of 0.8, and my yellow is when I calculated this in in Excel. So let's say if I change this, how it will behave. So if I do this 0, it will overlap with blue line. If I do this 1.2, it will overlap with my gray line. Right. So this is how you should do. You should not change your CG location in software and calculate the movements again and again. Now to calculate neutral point, we estimated it will be around 0.8, right? This 0.8. So let's say where this yellow line is horizontal, 0.9 or 1.0, 1.1, sorry, 1.1, 1.05. So this is my neutral point location. At this point, this line is horizontal, so this is my neutral point location. But how do you calculate this exactly? For that, we have neutral point formula with us, which is my when I calculate it at 0 CG, it is directly my neutral point location formula. I have to calculate the slope of my graph. This slope, the original slope for the CG location of 0. So this versus CMY total. So this is the slope. I'll only see the linear regions. Maybe I'll remove these 2 points. I have a linear graph. I'll just add a trend line, linear, display equation on chart. So y is equals to mx plus c. So my slope is 0.0411. But again, the problem is I don't want versus angle of attack. I want versus CL. So CL versus CMY. So CL versus CMY. Now I will plot the trend line, display equation on that. So this is my slope. So it is about minus 4.666. So my CL is minus 4.666. Now my neutral point will be is equals to negative of negative negative of my CMCL multiplied by mean error. So you see, same thing what we did manually, 1.05, we are getting exact number 1.0555. So this is my neutral point location. This is the calculation to do given in Raymer, Goodmanson, as well as your Anderson flight dynamics. Now I got my neutral point location. Now I will define one more term known as static margin. Oh, before let's go to PPT and see. So we have got my neutral point location, right? So this is the neutral point location. In this you see NEU. This is my neutral point. Ahead is my CG. So the distance between these two is my static margin. The same graph we plotted, right? The green line you see here is my neutral point location. If I make my CG ahead of my neutral point, that is my static margin is positive. So I have uh, positive static margin with the slope increasing in this direction. If I'm using negative static margin, then I'm going towards the unstable configuration. So this is the stability curve what people expect. So this is CMY versus CL. So that's why we took the slope between CL and CMY and not angle of attack versus CMY. So this was all about stability. Static margin, you can just, take the percentage. Now define the static margin as, I want a static margin of 20%. So your CG location will be, neutral point minus static margin. It will be neutral point minus static margin in percentage. So divide by 100. We need to multiply with MAC as well to make it non-dimensionalized into MAC. So if I use this CG location, I have the static margin of 20%. So this is how you should do your stability analysis. Now, if you want to change your static margin to 5%, you can do that. 20%, 30%, your CG location will change. Now, as a designer, it's your job. Once you defined your static margin, now it's your job to make CG such that make your aircraft such that your CG comes to this location, which is 0.9. If you are, this is a tandem wing aircraft. This is a tandem wing aircraft. So my neutral point is about 1 meter. Okay. So I will go to top view. This is top view. I'll go to model, measure, add. This is 0.8 meter. So 1 meter. So this is, oh, sorry, from this to this. So 1 meter. So this is the location of my neutral point. So if I want stable configuration, my CG will be here. If I want unstable configuration, my CG will be here. If I want neutrally stable, my CG location will be here. Now you need to make sure that you place all your electronics, payload, empty weight, such that your CG location comes around this point. You need to move your battery maybe backwards, or uh, take your battery at back and payload in the front. So you need to balance your CG. So this was all about the stability. Now for control part, once you select your static margin, you have your CG location. It is 0.98. Now it is fixed for you. Now I'll go to analysis. I'll fix this CG location as 0.98. I will not change this. Now my task is to do an alpha sweep, beta sweep. So I'll perform alpha sweep here. I'll perform beta sweep. So let's say I perform alpha sweep is anyways already done. We'll run it again. So launch solver. Now we are calculating all the stability derivatives. So we will write stability derivatives. So now this is for alpha sweep. We'll run beta sweep. So beta sweep means we'll run at 0 angle of attack, 1 point only, beta from minus 10 degrees to plus 10 degrees. So plus 10 degrees. Prepare solver. Prepare solver, launch. And what stability derivatives we actually need? We need CL alpha, CM alpha, CY beta, CL beta, and Cn beta. You can calculate per degree or per radian according to your wish. So we have longitudinal stability derivatives and lateral directional stability derivatives. So copy. So now I can plot, angle of attack versus my CMY, angle of attack versus my CL. The slope of this will give you your CL alpha. Then you can plot angle of attack versus your CMY. CMY, and make sure you take the linear region. You take the linear region only. So this is your CL alpha, CM alpha, and in beta sweep you need to plot your beta versus I think this is shifted. Beta versus side force. So side force is in y direction. So this one, CY total. Insert. Yeah. So this is how the graph will look like. And next is beta versus your L, CL. So your CL is CMX, CMX total. This is your second graph. And your third graph will be beta versus your CYZ, CMZ. So this is your third stability there. So you calculate the slope of this, and this and this, you will get all these five stability derivatives. So these are static stability derivatives. There are also something known as dynamic stability derivatives. Now control. Now this was all about the stability. Now these stability derivatives will be used in your sixth of equation of motion. So when you actually model your flight dynamics and you want to see how your flight behaves in a simulator or in actual environment, so you put these numbers in your sixth of equations of motions, and then it will simulate it in the simulator as well. So next is control. So for control, what we do is we put the control surfaces on wing, aileron, rudder, and we deflect, we generate all the aerodynamic loads and see how they perform. So if I'm deflecting my elevator downwards, what it should do? Deflect my elevator upwards, so it should give pitch up movement or pitch down movement. So how it behaves, that's what we have to find out. So for that, what we will do, we'll define control surfaces in our aircraft. So this is my aircraft. I'll remove this measure, delete all. So for aft wing, let's define the elevator. So I will go to subsections. Here I can go to line control surfaces, add. Now my control surface has been added. I can go to, now you can from here start U and end U. I can change this location of elevator. I can change the end location of elevator. I can change the length of the elevator. Let's say I select this length. Okay. Now my elevator is defined. Now how to analyze this? I go to analysis, VSP arrow. Now I go to control grouping, add. Now these two control surfaces has been added here. I'll select, I'll add all. It has been added. Now 0, 0 means they will move in. See, right now the direction is opposite, right? If I do this -1, Okay, it is not updating here, but this -1 and 1 represents the gain. So if I want to deflect it 5 degrees in downward direction, what I will do is I'll do this 1 and -1 so that both rotate in same direction because it is an elevator. If this was a aileron, it needs to be rotated in opposite direction. So one upward, one downward. So it will be 1 and 1. For elevator, it will be -1 and 1 because they want to move in same direction. Now, once this is done, -1 and 1, I'll go to overview. Here you see one more group has been enabled, which is known as control group angles. So I'll select this, let's say 10 degrees, prepare solver and launch. I think some issue, I think it is stuck. Yeah. So what is the issue? Analysis is error, prepare, launch. Hmm. I think some issue. Let's see. Okay, there is some problem. Let's take a simple model and see if we are getting the same error. So if I take a wing configuration, let's say I want sweep of 0 degrees. I want taper of, okay, yeah, same issue we are facing here. Let's see a simple problem. Whenever you face a problem, just take a simple problem and see if there is no software problem, okay, because there are bugs in the software. So always take a simple problem when you're facing these kind of issue. I'll go to taper of 1. Okay, I'll just do this analysis. I'll I'll make the elevator, add, okay, control grouping, add all. Right now, let's not give this any degree. Prepare, launch. Yeah, this is running. Now let's give 10 degrees. Yeah, see, this is also running. So if you see the lift distribution, okay, means software wise, there is no issue. Maybe there is some problem with our model, some convergence issue it is facing. Let's delete. Without control surface only we'll see if it is running or not. Yeah, without control surface it is running. As soon as we add the control surface, there is a problem. We'll wait here. Hmm, yeah, it is running. Again, let's add the control surface. Add. Okay, I will not add here right now. And without adding only, we'll see if it is running or not. So this is what you have to do. Don't do all the things at once. You'll not understand what is what problem, which part is creating the problem. So this is also running. So I think as soon as we add the control surface in the control grouping, it is not able to run. So if I add this, okay, let's see in opposite direction. I think now it is running. We'll see. No. In same direction also it is not running. In opposite direction not running. Let's change the CG location. Please. No, it is not. Okay, let me see guys what problem, why this problem is arised. I'll upload the new model. I'll make sure that I upload the new model which is free from all this issue. So right now what we will do is we'll take the simple problem to just tell you how these control derivatives are found. So again, I'll go to this problem as this was running for us. I'll add the control surface. What I will do is I will run the VSP arrow for with no control surface for now. So control grouping, I'm not add. Let's add this and minus 1 and 1 so that they turn in same direction. Right now 0 degrees from model. Let's say minus 4 to 20. This will be 13, 0.1. I'm just running a simple problem. Sometimes there is a version problem also. So we can try this in older version as well. So if I have this, open this in older version. So you see the GUI is different. So this is the older version. If I add the control surface here, add all, minus 1, 10 degrees, run. Mesh not closed error. Yeah. So this is the error we are getting, mesh not closed. I think the problem is this, when we are designing the control surface, this point and this point are not overlapping, which is creating the problem. Let's see if we can solve this here. Hmm. Let's see if this solves the issue or not. File, save. Again, I will run 10 degrees, control grouping done, -1, 1, launch solver. Let's see. Okay, still the same error. I'll see, guys, what is the problem behind this. I'll put this in uh, uh, our group discussion why this problem was there. Let's go to our simple wing problem. Okay, for some reason this also did not run. What I will do, I'll close all this. I'll close open VSP. I'll open it again. Wing. So I'll add the control surface. Control surface, add. Okay, it is added now. Control grouping, add all, -1 from model, 10 degrees, -4, prepare, launch. Okay, I'll go to the results. So the results will be in the, as this is the unsaved file, it will be in the file location where it is present. I'll just go to that file location. Here one polar file will be generated, this one, edit, copy. So control derivatives. So I've only run these cases. It's fine. It's fine. So I can plot angle of attack versus my CL graph, and angle of attack versus my CMY graph. My CMY is CMY. So this is the graph. Now this is for delta deflection of 10 degrees. Now I will run it for 0 degrees. I'll run for 0 degrees. So prepare solver, launch. Now you see my lift distribution is elliptical, but before it was, because of control surfaces, it was not like this. Now again I will reload this, copy, I will paste. Now this one was for delta of 0. So del 0. And this was for del 10. Okay, I'll plot this. Add angle of attack versus CL. And add angle of versus my CMY. So this is how you get. This is what we expect when we deflect our control surfaces. We deflect our elevator. Okay. Now how to find these derivatives? Now you see first derivatives for CL delta E, CM delta E. So we can find CL delta E as CL2 minus CL1 divided by 10 degrees. So I can take as this, you can see there is a, it is linear. So it is not changing the slope. So I can take any value. So let's say I take at minus 4 degrees. So CL2 minus CL1 divided by 10 degrees. So this is my per degree. So CL delta E per degree. Similarly, you can find CM del E. Similarly, you can find when you give the rudder, when you, now this is just the wing. If I add the rudder also, so I added the rudder, just make it back. I don't want symmetry as it is a single part. I will rotate this about x-axis by 90 degrees. Just scale it down. I'll just scale this down. We'll go to subsurfaces, add. So now this control surface is added. I can rename this control surface as rudder. Again, I go to analysis. Now to calculate the rudder effect, I have to do beta sweep. So turn off the alpha sweep. 1, beta sweep from minus 10 to 10 degrees. Control grouping. Now this rudder control surface has been added. Add. So this has added. Now here you can give let's say 10 degrees. Now make sure you remove these two. These two. And run. Launch. Do it for 0 degrees, 10 degrees, and you can calculate CY delta, CY delta R, CL delta R, and CN delta R. Similarly, you add aileron, rotate them in opposite direction. You can calculate CY delta A, CL delta A, and CN delta A. So this was all about the stability, weight estimation, basic UAV sizing. This was all from my side, guys. Let me know if you have any questions, please. Next, we'll move forward is with the ANSYS Fluent for this model. Let me know if you have any questions. If not, maybe we can take break for 10 minutes. No need to leave the session. After 10 minutes, take the break and we'll start with ANSYS Fluent at 3:50. Okay, so no questions. So we'll take break for 10 minutes and we'll start at 3:50. And Rahul will start with ANSYS Fluent. So for the same model, he will start the how to export the CAD, how to do CAD cleaning, processing, meshing, solving, and then post processing. So okay, guys. So let's meet at 3:50 then. You can stay in the meeting.
Hello. 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 Hello, sir. Hello.
Hello guys, am I audible to you?
Yes,
Yes.
sir.
Okay. So far we have completed the OpenVSP and now we move to the ANSYS analysis. So let me share my screen.
Hello.
Hello, am I audible now?
Yeah, yeah.
Yes. So we have this geometry. So we'll export it like from this option, export, and then for CFD we need step file or IGEs. So we'll choose the step file as of now and then export. So I have already exported a CAD file here. Let's say I'll add them again. So you'll see a CAD file. Okay, location is different.
Rahul, untrimmed STP.
Okay, that's what. Okay. Then
No, the above option.
this one, right? And then, so see, we have a CAD model here. So we'll export this to Workbench. And okay, let me start from basic. So this is a Workbench environment. where it's an analysis software, so where we can do all sorts of analysis. So as of now, we are going to do a fluid flow analysis. So we'll choose a fluid flow fluent with a fluent machine. So we'll drag this option to our workbench where we'll have a geometry, mesh, setup, solution, and results. In geometry, we can have a we can import the geometry or create the geometry, and then we can create a domain, and then all sorts of the things which require the geometrical part we'll do in this option. Then we move to the step meshing, where we'll choose the surface meshing, volumetric meshing, inflation layer, boundary layer, and all. And so we'll create the mesh for the our geometry. Then we'll move to the setup, where we'll set up all the boundary conditions, fluid flow conditions, and all, and we'll run the uh, Fluent solver here. So we'll start with the geometry session and import our geometry from browse. And this is our evaluation. So we'll import this card here and then edit in space clip. So you see, this is the geometry we have. In Fluent, we generally deal with the solid body, but here you can see these are all the surface. So first of all, we need to create a solid body from these surfaces. So I'll start with the options here. We have a sketch modules where we can do all sort of sketching things. Then second is a design where we can do a solid body designs. Like we have a combine option, we have a fill option. It's like a SolidWorks or a AutoCAD we are dealing with. So if we can split the body, we can split the surface as well. Then second, this is the graphic related things. We do not need to go into that. Then here, this is the measure option where you can measure the size of a thickness or let's say airfoil cord length and all sorts. So once you select this point and then control and then select this point, you'll see the distance between these. So this tool is helpful when we are going to do the meshing. So we all we can have to uh, give the number of cells for the this section, trailing edge section. So if we have the exact length of trailing edge, then we can divide it to the number of cells here. Then second, the most important tool is the repair one, where you will repair the all this geometry. So as of now, you can see this is a uh, surface of the geometry. So we'll stitch this to so you can see the three stitches and all this. These are the basic information you can see here. And then once you the green tick, you create the three solid geometry. One is the fuselage, wing, and second wing. So this is the one geometry, but it is still not combined. So we have to combine this geometry from the design box. So once you choose the combine option, it will show the option of a cut and combine. So here the click an object to merge the target with. So it is let's say let's uh, select the fuselage and then this object. So you see there is a whole one body which is a solid body of our design. Okay. I will rename it. So for fluid analysis, we need to have a domain, fluid domain. So as of now, we are working in a student version, so we cannot make like a bigger domain So since bigger domain will have a large amount of cells, so we'll restrict ourselves to a smaller domain. But in general, we'll have to, like for wake, you can create like up to 20 times of a chord length of this geometry, where and in the radial size or upstream side you can have up to 10 times of a geometry size. But as of now, we'll create we'll restrict ourselves to the smaller size. So we'll go to the prepare option where we'll have an enclosure option, and then see if you select this body, which is already selected here, you see the enclosure around it. We can untick the symmetric dimension and create a domain of this. So yeah, before moving ahead, like we need to know the what is the chord size, what is the trailing edge. So let's measure it the chord size. Okay, so okay, for prepare option, repair, we can have a like we have extra lines here. We can check all those parameters. Let's say see the extra edges, which we don't require. So we'll remove the extra edges from here. There is no duplicate option. So now the geometry is uh, uh, error free, and we are good to go with the meshing here. So the chord length is around 225 mm. So what we'll do, let's 225, 226 in fact. Which 0.47. It's green line. Problem. Likewise, we'll calculate the wing 2 parameters. This is also 225. I think it's a same dimension here. Yeah. And second thing, you need to know what is the diameter of uh, this fuselage. Okay, so the length we can see 692. It's a circular length. Okay, 692. The reason why I'm writing this is like we do not need to go again and again to the geometry and like for when we are going to do the machine. So now we are good to go with the domain, creating a domain size. In a prepare option, we have an enclosure. We select the geometry and we see the automatic, we see a bounding box around the geometry. So let's say we are going to create a domain of a size, let's say 2 times of upstream. Also, we haven't calculated the length of a fuselage. So let's measure it here. This is 2400. So we can have 2400 times the times of length of fuselage, and then let's say 4 times if we make 24 times. If we are going to do analysis of a only wing, then we'll choose the chord size of a fuselage. But if we are going to do like full body analysis, then we define our domain according to the fuselage length. Likewise, 5800 upside. Another thing, you can short it out like we this is the symmetrical body. So we can always have a domain size which is like symmetry to the Z and X axis. So we can reduce the number of a cell and can have a like faster the calculation. So I'll choose like symmetrical boundary condition over here and reduce this to let's say 0 as of now, and then we'll change the length accordingly. Or I'll better cut it down. Okay, so as of now, we'll select this enclosure. So we have already created one enclosure and a geometry. If we suppress this geometry option, we see there is already a uh, void surface inside the our domains. So this is good. We can delete this geometry option now, and you can see we have a good domain. So I'll hide these surfaces. So we have a geometry which is void inside, and we have a full enclosure. Can create a mid surface. Finish. So the length is 33,000. So our span size is 2,000. 3,000 mm. So obviously our midpoint would be 1500 mm. So what we can do now is pull the option. See, we can change the limb now. So we'll write we'll go and say 1500 plus 4800. So see, we have this is the mid surface now. Up to this point, it is clear to you all. So now it's the time to group the name selection. We'll delete this name selection here and start with the okay. So we have a leading edge. These are the leading edge. So we will split the surfaces for the leading edge. So because we require a surface mesh in the leading edge side. So we select this option split, select on the surface, and you can see there is a two option percentage and lengthwise. So we'll try to choose the percentage because sometimes we don't know the length options. So it's better we deal with the non-dimensional part, like the percentage of a length or a chord size of a length. So as of now, I selected the 10% here, and see we have a one. Uh, we have generated we have split this. Likewise, if we do for the below side, we select the 10% and see. Similarly, for the second wing, 10%, and then select this surface and 10%. You can also split the trailing edge, but right now I'm not going to do that because when we split the trailing edge, we'll have a like huge number of cells, so it will be like, tougher to do in this student version. So as of now, I'm sticking with the leading edge splitting part. Now this is the fuselage. So fuselage. Wing one, leading edge. Wing two, leading edge. And this is trailing edge of wing one. Trailing edge. Wing, trailing edge. This is wing tip, or you can say flat surface of wing. I will rename it a wing tip. Wing tip. You can do wing Two green tick. Then we go and show all. Now it's time to uh, create a inlet. What I'll do, I'll also split this surface. I just know it is not required in platform. This is inlet size. This is outlet. This is symmetry wall. So I'll rename it symmetry because once we import into the meshing, these name selection will automatically go into the meshing tool. And these we have walls. Then, then. So we have completed with our geometry part. And we'll close it. See the green tick, it is automatically updated here. And then we'll move to the meshing. So we'll select this, right click, and we'll see the edit option. So we have 20 cores. So I'm gonna assign 10 cores. Hmm. So you always choose the double precision. Earlier, I haven't selected this option, so I had to close this fluent. So we'll go with the double precision. Hmm. Now we'll select the import job. See, you can see inside our geometry because see the direction. We need to have a accurate direction. So yeah, so this is our inlet here, and this surface is our outlet. This one. So as of now, we don't do the local sizing and check what we have a default option. So we'll update this and go to the directly jump into the surface machine. So there is an option of a custom field functions or control size. So for that, we need to import some file where we'll have a custom local sizing. But as of now, we are not doing the local sizing, so it's no. The minimum size it is automatically selected here based upon the geometry, growth rate, and size function. So we have a curvature and proximity. So curvature is generally where there is a some curvature of geometry. Let's say some with the radius of curvature r. But and the proximity option is when we have some gap. So as of now, there is a no gap between two surfaces. So we can select the curvature option, and we can go ahead with the generate surface mesh. So what you can see here, a warning generated to improve the quality. So we can do improve surface mesh or we can have a local sizing. But if you see the meshing of this geometry, I'll show you the surface mesh of. See. So why we have this warning? Because our trailing edge is very small and the size is not able to capture the trailing edge properly. Also with the problem with this leading edge. So there is a requirement of a local sizing for this. So as of now, we can directly measure this. What are the size we have? So we'll select this point option and there is a distance option. So we will select this point and see we have a 0.02 mm 2 meter 0.02 meter of length, this cell size length. So if we are working with the student version, there is a limitation with the number of cells. So I'll do what we can do is let's say make a course mesh and run the simulation. Of course, results will not be the exactly matching with our experimental results or whatever we have validation values, but we can set up the simulation here. And other options we have described the geometry. So we'll see the geometry consists of only solid region, geometry consists of only fluid region with no void, geometry consists of both fluid and solid. So we'll select this option because there is a no solid option object. Change the fluid boundary type from wall to internal. We'll will remain with these options and describe the geometry. Then see the domain wall we have already wall type boundary condition. The name we have given like that. It will select the inlet as a velocity inlet, pressure outlet, and symmetry as a symmetry. Of course, this is better. So there is a issue with that. So we start with the local sizing from. अभी वो इंग्लिश बोल रहा है. So we have a trailing edge length of 0.47 mm. So what we can do, write it in meter. So we'll split our trailing edge, like minimum number of a cell to be 3. So face size, name it as a trailing edge, and our trailing edge would be size by 3. Bring one trailing edge, add local size. We will also do the face sizing for leading edge. So for leading edge, we have already calculated 0.02 mm of a length. That was the default mesh length. So we will stick with the, let's say we can have a 0.05 in that area. And then see the what we have mesh size. This might take some time, I guess. See, now we have a 3 cells in trailing edge. Also, we have slightly improved our leading edge cell size. Obviously, we can go more finer here, but I would restrict ourselves to at this cell length, and we'll check the other surface mesh. We can reduce this size as well. Also, we can work with the this fuselage cell. But as of now, if we are going to run this on a student version, it will take a lot of cell size. So we go ahead with other option. See, we didn't get any warning size. That means we have a, okay, sir, we don't have a like worst surface mesh. I won't say it is a good enough, but we can work with this. So we update the reasons. See, enclosure is a fluid. Okay. Then about the boundary length or boundary layers. So there are various tools where we can determine what would be the first length of the boundary layer height. So I, so you can what you can do is just Google it, y plus calculator. So you see there are a lot of y plus calculator here, like Cadence have. So let's say if you are going to simulate at 30 meter per second, density, let's say 1.225, and mu is like that. The length of a chord size was 0.226. So we say 0.226 and y plus value 1. And then we compute. So that we have a Reynolds number and we have a first cell height. So we can copy this, select the uniform, select the first cell height. We give the number of a cell, number of a layer, let's say 7. But obviously we can give more than 7. Like, at max, we have a good boundary layer, number of a good boundary layer up to 20 to 25, or it can vary, but you need to know the what would be the length, boundary layer length. But as of now, we are going with the 7 and add the boundary layer. Now with the generate mesh, you see we have a fluent, and then there are options: polyhedra, polyhexacore, hexacore, and tetrahedron. So I'll select the polyhedra, then keep the first boundary layer height, and rest is the same. So there are the tutorials of ANSYS as well. You can always go and check in YouTube. We'll provide you the link as well. ANSYS Innovation. So in that you can see the basics of how to use the tools. You can always like go to the introduction, solution setup and all, and you can explore these the videos as well. Meanwhile, it is. I'll show you some quick tutorials. You can go to the playlist of courses and see the what are the courses available for the ANSYS. So this is the ANSYS P1. See the mesh generation, how to do physics setup, solution setup. So, so we have a warning here. Mesh has a minimum orthogonal quality of this. Insert the volumetric. So you can see the issues are with the surface, some of the surface size, and here the boundary size. So what we can do, you can change these sizes. So mesh generation is like a hit and trial. You have to see where are the issues and then you have to solve for those issues. Also, you can see there are the issue in the wingtip leading edge. So you can now reduce the size. You can select the curvature for this. And let's say give it 1 to 0.004. See, we have improved the quality of leading edge. And I can create the volumetric. There are still some warnings, but I think we can neglect it as of now. This won't be creating an issue with the mesh, with the simulation setup. So we'll close this. It's existing due to the license issue. Okay, so we have generated a huge cell here. and hence we cannot save this. So please exit this session and start another session. This is will cannot be so this is not in this. We have to input, I think we have been it 4 to 5 times. Okay, so let's close it. So what we can do is we can reduce the our domain size here. Information again. This is not closing. Let's save it. Hello, Priyesh. Let's we have saved something. There is some issue here. Yeah, so we have saved our geometry here. So what we can do, we can directly import this geometry. Language. We can see. So you can see the small boxes here. So this is the minimum size, this is the maximum size here. So now we can again See the mesh count. It is still too high for the this license. So like these are the options where you can always uh, go through that. You can always explore how to like get the good quality of cell by reducing the number of cells, by reducing the cell size. Anyway, this won't be going to work in like student version. So at max, what I can do right now, I can show you the fluent options where you can learn how to set up the fluent environment. If I think it won't be work here. Let's say save it. If there is issue, then see. Like there is a license issue here. So anyhow, we reduce the things. The things will like going to a bad cell here again and again. So for your sake, I can try a one again. Like leading edge, I can increase the leading edge size. The next step would be oh, leading edge is too. Okay, I have to. No, this is correct. So what I can do is can click to here. Let's say we did one. Let's change it. Actually, so we are already working. We can even reduce this size. Okay, existing to have 2.2 million. So yeah, we'll have a number of cell issues. But you see, we have a mesh here now. If I insert clone, see, so we have a good trailing edge, but the section over here is still too, the cell size is too high. So we cannot go through with this like full CFD simulation. But yeah, as of now, we cannot save this mesh because of the license issue we cannot go ahead with this. But I can show you the what are the options we have in a Fluent, and then by this we can close our this session. So let me close this. I don't think so. It will save here. Now we have to import some mesh file. Priyesh, are you there?
Yes.
Uh, can we create a geometry like, on a wing, or we can? Do we have any mesh file here in your setup?
Um, let me
Without
think.
importing, I cannot show them like what are the options here.
Yeah, you can go to OneDrive users,
Which one?
OneDrive personal,
Mm.
IIT Kanpur,
Mm.
uh, semester, IIT Kanpur, users. You can go to Rahul, Fluent, try 3. This mesh file you can use.
This one.
Yeah.
Would it be a huge one? Okay, let me run. Don't we have any airfoil here?
You want OpenVSP location?
Uh-huh.
Go to Start, Windows.
Hmm.
Right side beside Google, you can see VSP exe. Right
Where
side, right side, right side.
with this?
Yeah, yeah.
No, the one where I have saved the geometry. Yes. So this is the mesh file now we have. Uh, we can import, what we can do is we can import the mesh file. Priyesh,
Yes, Rahul.
uh, where's the like, file, like OneDrive one? Cannot see here.
Uh, can you minimize the Fluent?
Huh. So this is the file we have, mesh file.
Huh?
I want to open this in Fluent.
Yeah, so just copy this path.
I think by dragging it works.
No, I don't think dragging will work. Copy this file path.
Ah, it's reading the mesh.
Yeah.
Huh. Okay. So now we have imported another mesh file. Uh, this was created long back ago. So here, this is the symmetry. So I'll show you with the start from the start. So this is the journal where we set up the solver type, pressure based or density based. In our case, we usually work on pressure based since Mach number is not going to vary that much. Velocity formulation would be absolute, and we are going to do a steady simulation. So these things are okay. If we are going to do a transient, then we'll select the transient option. But right now we are going with the steady, so we are going to select that steady solution. Then for the models, we are like if we are going to do some energy calculation like in thermal calculation, then we'll double select and then we'll on the energy equation. But we are not solving energy equation as of now since it is an incompressible solution. So the energy equation won't be like come into the picture. As far as the there are options in visit, laminar, spalatameras, K epsilon, K omega. In K omega, we choose the SST model and production limited. These are the like default options. So we go ahead with that. For K omega SST model, there is a y plus value that should be less than or equal to the 1. But in K epsilon, we will see the near wall treatment where we see the standard wall function, scalar wall function. For that, you need to have a y plus greater than 30. So for safer side, you can have a y plus value of around 100. So what the K epsilon do with the standard wall function? We have a model for the wall. We do not actually solve the boundary layer equation, but we solve through the some models. That is the representation of that the standard wall function or the scalar wall function. As of now, we'll go with the k omega and then hit OK. Rest is fine. Then we go to the material. So in material, the fluent zone will have a the density as a constant and viscosity we have here. Likewise, during the y plus calculation, we have given the mu and the density of array 1.225 and the viscosity value. That is exactly the same thing. You can always change this value. Let's say if I go to 1.2 and click the change or create. Also, you can change this density as well, like 1.81, then select create and then close. Then you see the cell zone. So this is the fluid zone here. Inside we have our model. So this is the one model. So this is the one UAV, and we are going to simulate here. So and the all the other boundaries, these are the uh, inlet and outlet condition. Then in cell zone we have fluid boundary condition. We'll double click here and see this is the far field. So we can have a various uh, boundary conditions. Uh, Far field is selected here because we wanted to like check whether this, if you are unsure about what should be the boundary condition, then you can always have a pressure far field as a boundary condition, making your far field enough for this boundary condition. In here, we can click the edit. You can convert your velocity to the Mach number and select the coordination system as a X, Y, Z. You can have a flow direction as a one, like X direction is one here and Y direction is zero. So this represents the angle of attack of 0 degree. But if you have you want to put some angle of attack, let's say this is our plane. So XZ plane. So angle would be changing from like X and Z only for Z component. So you can compute the uh, angles like let's say 4 degree and trigonometric of sine. This is let's say this is a sine value. So when you see the direction of uh, let's say this is your body and this is your angle of attack. So your component would split is like X cos alpha and Y component or Z component Y or X sin alpha. So in Z component there will have a sin alpha. So we'll put the Z sin component in Z value and cos component to the X value to better representation of a angle of attack of 4 degree. Again, you can see the turbulence intensity. You can put it as a default value and apply and close. In symmetry, it is a symmetry condition. So you need not to edit anything. Other than that, we have walls. In wall motion is stationary because there is no motion on a wall surface. Then slip condition as a no slip condition, that is also a boundary condition. And that's it. So this is all default here, and you will see it is same for all the walls here. So then after the boundary condition, you can go to the reference value. You can compute it from the far field. So when you compute it from far field, you have a area, that is the, you can always give the reference area density we have and also the reference length. So for reference length, we can choose the chord size. So we have a chord size of 0.226 and likewise you can select the planar area of a beam. as of now it is 1, but you can calculate the area of a wing, planform area of a wing. So these values are generally used for non-dimensionalizing the quantities like drag force, lift force, etc. After that, you go to the methods. You can go ahead with the simple, select the green gauss node based. You can explore all those three options. Always, you can also go with the least square on any of three. I'm selecting the green gauss, pressure second order, and that will be the default. The second order conditions, like these are the discretization over the pressure and momentum equations. So we are choosing the second order, at least second order discretization schemes. Then go to the control. That is a default case. You can always like reduce or increase this value, but I would recommend to not to like disturb as of now until you know what you are going to do with that. Then create a report definition. Here you can have a report definition of a drag, or better to go with the force calculation. So in X direction, we will have a drag force. Select all. So we are going to simulate for angle of attack 4 degree. So drag will also be the direction of the velocity direction. So the X will exactly have as a cost component here. And sine component will be in the Z direction. Create an output parameter and okay. Likewise, force in perpendicular to the velocity vector. So, so for velocity vector, also for lift will be created in this direction. This is alpha. So when you this is cos and this is sine. So sine component will go in X direction, cos component will go in Y direction. Create output and okay. So likewise, you have created the definition of a lift and drag force. And you can select the residuals. In residuals, it is a 10 to the power minus 3. You can also increase the criteria. Let's say 10 to the power minus 6 for all values. And click OK. Then we go to the initialization. Hybrid initialization and standard one. So in standard, you can select from far field. Also, do we like given the far field condition? Let's just in far field we haven't like it is a default 0.6. Let's say we are going to simulate in 30 meter per second. 30 divided by let's say 340 speed of sound. So it's a 0.088. And put it and apply. Then initialization far field. And initialize it. So it is done. मैं बोल रहा हूँ Unmute. Okay. Okay. So we'll after that we can hit the run calculation. Number of iteration, let's say 100, and then calculate it. So this is all overall the setup here. Uh, we this might not be like it may show the divergence or a convergence anyway, but anyhow we can we can go through all these options and explore in the fluent innovation courses here. After the one or two iterations, we can stop the simulation here and see the contours we got. If you have any doubt, you can ask directly. Hello.
Participants, do you have any doubts? Rahul, I think participants do not have any doubts.
Okay. So what we can do is we can put up a discussion forum here, and for the regarding the meshing or any of the solver doubts, we can solve it during that time. Okay. Sure, sir.
Yeah, fine. So can we close the session now?
Yes, sir.
Okay, thank you, Rahul and
So
Priyesh.
we'll
for
also
this
put some
wonderful session.
resources for where students can learn the Fluent or OpenVSP.
Yes, you can post it in the announcement section.
Hmm. Yes, sir.
Okay, learners,
With
we are
this,
closing the session now. Thanks everyone for actively participating. We are closing now. Thank you, everyone.
thank you so